Well, here is a linear approximation problem. So I've got some function f, and maybe I don't know that function immediately, but I know its derivative is equal to the function's value, say at all x. And let's suppose that I know this function's value at 0, so this function's value at 0 is 1, and then my goal is to find f of 1. Now, we secretly know something, right? I mean, I secretly know that this function is really e to the x. So when I say find f of 1, I really mean that I'm trying to calculate e to the first power. I'm trying to calculate e. The point here, isn't to say that the answer is e, right? The point is going to be to try to approximate this quantity without actually knowing the value of e. We already know how to do this. We can use linear approximation, right? I want to know what f of 1 is, and by the linear approximation business, well, it's not equal to, but it's approximately the value at 0 plus how much I change the input by times the derivative at 0. Now I know the function's value at 0, is 1, and since the derivative is equal to the value everywhere, that means I also know the derivative at 0. So the function's value is 1. The derivative at 0 is the same as the function's value at 0, which is 1. 1 plus 1 times 1 is 2. So approximately, f of 1 is 2. And since I secretly know that this function is e to the x, I'm saying that e is about 2. 2 is a terrible approximation, but we can do better. If we can do linear approximation once, we can do it a bunch of times. So instead of just jumping all the way to 1, let's first approximate f of 1/2. And that'll be f of 0 plus how much I wiggled by, which is 1/2, times the derivative at 0. Well, f of 0 is still 1. 1/2 is a half, and the derivative at 0 is still 1. So this is 1 plus a half. This is 3/2. Now we use that approximation to approximate f of 1. Yes, I'm sort of bootstrapping up here. Now I want to know f of 1, at least approximately, but instead of starting at 0, I'm going to start at 1/2. So that'll be about f of 1/2, which admittedly I don't know, but I've got this approximation for it, plus how much I change to go from 1/2 to 1 times the derivative at 1/2. Now f of 1/2 is approximately at least 3/2. 1/2. Now the derivative of 1/2, I don't really know what it is, but I still know that the derivative is equal to the function's value, and I've got an approximation of the function's value. So I can use that approximation here. The derivative at 1/2 is about 3/2, and now I've got 3/2 plus 3/4. That ends up being 9/4, which is a slightly better approximation to the function's value at 1. I mean, 9/4 is closer to the actual value of e. Well, if 2 steps worked better than 1 step, 10 steps will work even better. So here we go. Let's approximate this function at point 1. Well, that's approximately the function's value at 0 plus how much I change the input by times the derivative at 0. And the function's value at 0 is 1 plus 0.1 times the derivative at 0, which is 1. So approximately, e to the 0.1 is about 1.1. Now I repeat this process. I want to know approximately what's the function's value at 0.2. Well, that should be about the function's value at 0.1 plus 0.1 times the derivative at 0.1. This is approximately. The function's value at 0.1 is about 1.1 plus 0.1 times the derivative at 0.1, which is about, no, it is in fact the function's value at 0.1, which is about 1.1. So 1.1 plus 0.1 times 1.1, that's kind of a mouthful, but that ends up being 1.21. Now to approximate the function's value at 0.3, right, I'll start with the function's value at 0.2. I go from 0.2 to 0.3 by adding 0.1, and then I multiply by the derivative at 0.2. The function's value at 0.2 is 1.21 plus 0.1 times the derivative at 0.2, which is also about 1.21, and 1.21 times 1.21 plus 0.1 times 1.21, that's 1.331. Now, you might begin to see a pattern here, right? 1.1, 1.21, 1.331. These are pieces of Pascal's triangle, really. I mean, and that makes sense considering how I'm adding the number plus 0.1 times the number. Let's just keep going. So let's compute f of 0.4, that's f of 0.3 plus 0.1 times the derivative of 0.3. Well, the approximation here for f of 0.3 is 1.331 plus 0.1 times 1.331, which is 1.4641. Now I can do this again to get an approximation for 0.5, right? I'm really just taking this number and adding 0.1 times it, and I get 1.61051. I can do the same thing to approximate 0.6, and I get 1.771561. I can do the same thing to approximate 0.7. I take this number and add this number times 0.1, which is 1.9487171. Do the same game to approximate f of 0.8. So I take this number and add 0.1 times this number, and I get 2.143588881. You can do the same thing now to 0.9. So this number plus 0.1 times this number, and I get 2.357947691. And at last, I take this number and add 0.1 times this number, and I get 2.59374244601. Approximately E. Well, not so great, but I mean, it's, much closer than my previous attempts where I just used 2 steps, so using 10 steps is better. This technique of repeated linear approximation has a name. So instead of calling this, repeated linear approximation, people usually call this the Euler method. Let's summarize the algorithm. So here's a setup. I've got a formula for the derivative of f, just in terms of f and x. So this cloud represents some formula that involves f of x and x. And that's my formula for the derivative of f at x. And let's say I know the value of f at 0, just some number, and suppose I've picked some small number h. Well, what Euler method tells me to do is if I want to know f of h, well, I don't know how to do that, right? That's just linear approximation. It's f of 0 plus h times the derivative at 0. I can use this formula, say, to calculate the derivative of f at 0, and I know the value of f at 0, so I can get an approximation to the function's value at h. But now the neat thing is I can keep playing this game, right? If I want to know an approximate value to the function at 2 times h, well, that's about the function's value at h plus h times the derivative at h. And now I know the function's value at h approximately, and I know the derivative at h because I've got a formula for the derivative in terms of f and x, and I know how to calculate f of h approximately, and I know x, right? It's h in this case. And that means that I can get an approximation to f of 2h, and then I can just keep playing this game. If I want to know f of 3h, well, that's about f of 2h plus h times f prime of 2h, right? This is that linear approximation formula again. To go from 2h to 3h, I add h. So f of 3h is approximately my function's value at 2h, which I've already approximated, plus how much I change the input by, times the derivative at 2h. And this I can also approximate because my formula for the derivative just involves things I already know, at least approximately, right? I know the value of f at 2h approximately. And I can just keep on repeating this to move myself further and further to the right and, approximate values of the function that are potentially very far away from 0. The cool thing here is that I'm using, linear approximation at each stage, and that I'm using the information from previous stages not only to approximate the function's value, but also to approximate the function's derivative. I should warn you that in the real world, people don't really use the Euler method so often, but like any really great mathematical idea, there's a ton of different riffs that you can play on this basic framework. For example, since this is just going to end up being an approximation of the derivative anyhow, it's sometimes better not to pick a point which is all the way on the left-hand side of the interval that I'm approximating over. So sometimes you'll see that, say, instead of using 0 here, I might use h over 2. Instead of using h, which is really on the left-hand side of the interval between h and 2h, you'll see that sometimes people will use, say, 3/2 h, which is smack in the middle of h and 2h. And say instead of using 2h here, people will sometimes use 5/2 h, which is right in between 2h and 3h. So you can play some games, say, by choosing a different point to approximate the derivative at. And using the midpoint is sometimes better. Incidentally, if you've got some programming experience, I'd encourage you to try to write a program to do the Euler method. It's really fun to be able to see these calculations come alive.